Hi, good morning, everyone. My name is Itzel Vazquez from the University of Manitoba. Here's the disclosure of my funding. Thank you, ILSI North America, for the support for my research. I'm working for the Richardson Center. Quick review for everyone. I'm going to talk about allele and polymorphisms, and I want to touch base and explain what is the meaning of a polymorphism. A single nucleopolymorphisms are the most common variation in our genes. You can see here the nucleotide as our unit is structured in our DNA. So when you have a pair of alleles that represent a gene, and most of us, we all normally talk about homozygous, heterozygous. Well, that means that when you have two different alleles, it's called heterozygous, and when you have normally two copies of the same allele, we call homozygous. This difference in our genome makes a huge impact on our health. Some alleles are being related for a reduction of a disease, or in this case, study cardiovascular risk factors. Some alleles have been related to the decrease of coronary heart disease, but other alleles can be also related to an increase of disease. The key part of my research is to understand how our diet could change that association between our alleles and the risk of any disease. As I mentioned, our previous speaker, the field of genomics is growing pretty fast, and we now understand more about the impact of rare alleles that could have a small impact in our genome and our phenotype. But also we have a huge amount of common alleles that have been described in the literature. They have a small impact on our phenotype, but also there are so many associations that as they become stronger to identify this gene-diet interaction associated with a disease. So now all the data is getting cheaper. Now for the cost of analyzing the whole genome is like a reduction of $45. But also the technology is increasing to allow us to analyze more number of SNPs related with association. So now artificial intelligence machines are giving us the tools to be capable to interact and understand all those connections between the SNPs in our phenotypes, or even including our diet. Also, the analysis is changing so fast that we're moving from a single analysis, analyzing just one SNP, to have the possibility to explore combination of SNPs interactions, like using a specific software like Plin and Plato or R-squared scripts, that allow us to understand the impact of two SNPs, three SNPs, and the models that I'm going to present today allow us to explain a combination of SNPs that could explain the phenotype. So all of these new methods that allow us to understand how many genes interact, as you can see in this slide, based on the literature, we understand that so many genes interact in the phenotype, like for example, total cholesterol, LDL, HDL, which are the lipid profile. But also we have specific genes that interact to each other. So what we want to understand is, okay, how we can put all of these together to explain the phenotype of a person, to have the possibility to explain, okay, this person going to a dietary intervention is going to, at the end, benefit from the diet, or is going to actually make it worse, or definitely not have a response. We know the cardiovascular disease is the main cause of deaths around the world. And there's so many factors that you can modify, including your diet. But we understand that to understand the impact of your diet and the lipid profile, a huge component is your genetic profile. So we know that even we consume exactly the same diet, we don't have the same response. And that response is like locked in. The key to answer that question is in your genotype. So based on that, the objective of my research is to understand how a combination of SNPs could explain the variability of the response after a dietary intervention. And my focus in the diet is specifically dietary fatty acids. So what I'm using in this research is the partial least squared models. That is just a linear regression model, but a more sophisticated way. So in this linear regression model, one challenge is that we have different SNPs that could be associated, they have an interaction between of them. But the partial least squared model will allow me to understand the interaction of the lipid profile that we measure and a prediction value that could be created from the SNPs. So the most important thing is that R-squares for this model will explain the total variance of the data. So these models have been applied before for personalized nutrition. One of our collaborators from the University of Marseille in France, he already explained different profiles related with the diet. He identified, in this case, you can see this table, 70 SNPs related explain the 63.5% of the variance in cholecalciferol, a panel of 28 SNPs and 16 genes explain 72% of the variance in lycopene response, 25 SNPs that were explaining 69% of the variance of beta-carotene, and 42 SNPs explain 88% of the variance in response of dietary fat. So what this means is, like, if you understand a small number of SNP, you're capable to explain the variability after a dietary intervention. If you think a nutrient, a food, also could be considered as a drug. You're ingesting that food, your absorption, consumption, and you're gonna have a specific level, like a specific hour that you're gonna have the high increase in your blood, and then all of that, the nutrient is gonna go inside and metabolize. So it's the same application that we're using here in nutrition, that we wanna know after you consume a specific diet, based on your genetics, how high is that variability in your blood that you can identify after this dietary intervention. So with his studies for the Dr. Demarchelier, the important thing is, like, he identifies 6 genes that could be they can be used to identify the variability after intervention of carotenoid. So instead of, like, analyzing millions of SNPs, we're going to be able to identify only 6 or 7, or have a small panel of SNPs that can definitely transfer to clinical practice to identify, okay, is this participant or patient requires more carotenoids in their diet, or, like, their diet is correct. I think using these methods, eventually you're going to have another clinical tool that can analyze the quality of the diet. So based on these, we apply the same tools in our studies at the Richardson Center. So I was in charge of running a secondary analysis of 2 data sets. These data sets, they're clinical trials that previously they were already published. One of the data sets is one that I call dairy data. So these data contain, like, 20 SNPs, and the second data set, there's something I'm gonna call cheese data. It's a diet after, you can see, 5 interventions. They identify changes in total cholesterol and LDL, and identify this database, they consume, they have, like, 22 SNPs. So I'm going to explain the data, the dairy data first. It was a study that was published in 2016, and you can see here that after the dietary intervention with dairy products, you can see a small population that actually decreased their total cholesterol and LDL. But you can see that at least 60% of the population, their LDL and total cholesterol actually had an adverse effect. They have an increase in total cholesterol and LDL after dairy products. So these changes, actually, they were related with the genetic profile. Only a small group with this specific pattern, they actually were the ones showing a decrease in total cholesterol. However, you have a big population that actually, different data sets, if they were homozygous or heterozygous for other combinations, they show an increase in total cholesterol. But my big question here is, like, okay, I don't only want to identify these individuals who benefit from dairy products. I want to understand and identify the person before a diet intervention. Is this person going to have a decrease in total cholesterol before, after the clinical trial, or after? So applying linear regression models explain the variability and the variance in all those groups across. So this is the preliminary data that we have. Right now, using this panel of 20 candidate SNPs, we identify 32% of the explaining the variability in total cholesterol in response to dairy products. You can see here the BIP numbers is what we call the score. What this model is doing is organizing all these SNPs, and it will tell me which ones are the most important that contribute to the model. So if you see everything that is above 1.0, those SNPs contribute the most to the model. So you can see here that we identified a panel of A SNPs that can explain the changes after their products. Also, you can see here, thank you so much, that after this analysis, one thing that we were really excited to see that after our analysis, we can see that still two of the genes were strongly in the top 5 of these SNPs. So actually it replicates the studies that were previously published, and they give us really a good feeling that we are on the right track to identify those key elements or key SNPs that could explain the changes after a dietary intervention. So the second data set contained like 68 participants. They went through different dietary interventions. I'm not going to explain this study in detail because the lack of time, but I just want to mention that we explored the data using 2 different groups. One group, we merged the data with MOFAs and PUFAs against the saturated fat. So at the end, we were trying to mimic these 2 data sets to be the same, like trying to analyze the data in the same way to explore one data set, create a model to explore the second data set. And I will explain that later on. So here's the preliminary data with our second data set. One more time, 20 different candidate SNPs explain 27% of the variation in total cholesterol in response to dietary saturated fat coming from cheese and butter. So we were excited to see that we can see a trend between 2 data sets, these 2 independent data sets, showing the same SNPs, for example, ABCG5, and we have this DHCR7. If you remember, they are the 2 genes that were published in our previous analysis. So once that you compare these 2 analyses, you can see that we have 6 SNPs that could explain the total variability and total cholesterol in response to dietary fats. So what we did, we were trying to create different models. Now, our collaborators have created a prediction model to use one data set as a test data set and explain the changes in the second data set, using dairy 1 and apply that partially squared model in the second data set. However, at this point, we don't have validation of the models. Like right now, I'm showing preliminary data explaining like how these 2 different models explain changes in total cholesterol in 2 independent data sets. But you can see here that the key elements of the SNPs that were replicated in both data sets. We identify BCG5, also CYP7, and those 2 genes in particular that were replicated in one set, and they were also showing up in the second data set. So this tells us that definitely we can, instead of exploring multiple genes, we can identify a small panel of genes that they can later on apply to clinical trials, and they can apply as a clinical diagnosis of how do you respond to dietary fat. Are you going to benefit for consumption of dietary fats, or are you going to have an adverse effect? So the talk message, the conclusion of our study is like we definitely created a prediction models that explain the total variability of the blood cholesterol. However, the accuracy of the models of this model is at this moment is really low. And one limitation is like we start using a candidate SNP approach. At this moment, we are trying to go and get the whole GWAS data so we can build different models that explain higher variability. And that's the validation steps that we are right now. So I have to thank the group of my collaborators, Dr. Jones, who is my mentor at the Richardson Center, and all the people involved in the studies that have been helping me to put this data together and creating the validation models. Did I get too short?